Hi, and thank you for joining me for this talk. My name is Michalis, and in this talk, I'll present to you a couple of different dynamic partial reduction techniques that we can employ for programs that have spin loops. And I'll start by explaining what dynamic partial reduction is on a very high level and why it doesn't work well for spin loops. So, dynamic partial reduction, or DPOR, is a highly effective way that we can use to verify safety properties of concurrent programs. And the main reason why DPOR is very popular is because it does so without explicitly storing the visited states. Now, one major drawback of DPOR, on the other hand, is that it actually doesn't work for programs that have loops. So if we want to verify a program that does have loops, what we have to do is bound these loops or manually unroll them. However, bounding is expensive. And this is especially a problem because in principle, we want to use larger bounds in order to be confident that our program is correct. But a bound that's greater than 1 can actually lead to an exponential blow-up of the state space. And do not take my word for this. Let's take a look at an example. So here we have a reader-writer lock implementation. This implementation is extracted from the Linux kernel. And let's try and verify it using a state-of-the-art DPOR implementation. So as you can see in this table here, for a bound of 1, the verifier needs less than a second to verify it. For a bound of 2, it needs about half a minute. For a bound of 3, it needs approximately 20 minutes. And for a bound of 4, it exceeds our 30-minute timeout. So what is the issue? Why is bounding so expensive in the case of DPOR? The problem is that DPOR will explore the possibility of each of the program's spin loops failing from 0 to b minus 1 times where b's are bound. So what is the problem? What is the solution? How we can solve this scalability issue of DPOR? Well, the solution is actually simple. The solution is to bound all loops using a bound of 1. But this solution is not sound in all cases. So for loops where increasing the bound will get us to the exact same state and will not produce any new behaviors of this program, then of course we can bound it with a bound of 1. But for loops where increasing the bound will also produce new behaviors that we'll have to explore, bounding with a bound of 1 is of course not sound. Now, as an example of a case where bounding with a bound of 1 is sound, let's see this particular program. So here we have x initially being 0, and we have this loop reading x until it reads a non-zero value. And of course, in this case, it doesn't matter how many times this loop fails, because all we care about is the non-zero value that this loop will read when we exit the loop, right? We reach the exact same state every time we complete an iteration if we read a 0 value. Now, such loops have already been pinpointed by existing work, actually, and they are transformed into what's called assume statements. So this assume statement here says read x and assume that the value is non-zero. So if the DPOR reads x and it reads a 0 value, then it will just drop the corresponding execution. But what if we have more complex loops? What if we have loops that do have side effects or potentially have side effects sometimes? Like, for example, they may have stores or some compare and swap instructions or some fetch and add instruction. What can we do about those? When is it sound to bound these loops with a bound of 1? And actually, this is where we come in. This is what this work is about. In this talk, I'll present to you Saver, which is a Spinloop-Aware Verifier. This is our extension to DPOR that automatically locates loops that can be bounded using a bound of 1 in a sound manner, and it does so. So in this talk, I'll describe 3 different categories of loops that Saver can handle, namely effect-free loops, that is, loops that have no side effects, potentially effect-free loops, that is, loops that may have side effects, but this is not known statically, and zero net effect loops, that is, loops that do have side effects, but these side effects cancel each other out, with the result being that we reach the same state when a full iteration is completed. I'm going to go over each of these categories during this talk, and let's start with effect-free loops. So effect-free loops are loops, the iterations of which will lead us to the same state, In other words, their iterations have no side effects. But what constitutes an effect-free iteration? Well, since DPOR does not store the states that it has already visited, in order to be able to know that we've reached the exact same state, we need to know first that the global memory remains unmodified, and second, that the loop only assigns at variables that are dead at the header. If the loop assigns at variables that are alive at the header, then every time we reach the header, we will reach a different state, and this is why we need this condition. As an example of a loop that satisfies these conditions, we can take the do-while loop of the introduction, and to see that this satisfies both these conditions, we can take a look at its control flow graph. In this graph, we have two edges for this conditional branch here, and each of these edges is annotated with an assume statement. So if the value read here is 0, we'll take this edge, otherwise we'll have to take this edge. And it's easy to see that, of course, this loop doesn't modify global memory, but also there's no variable that's live here at the header. So what we can do, and what Saver does to bound this loop using a bound of 1, is that it employs what we call the spin-assume transformation, which effectively cuts this back edge of the loop here and transforms the loop into a read followed by an assume statement. This is essentially the same as bounding the loop with using a bound of 1. Now, as an example of a loop that doesn't satisfy these two conditions, we can take a look at this loop here, which just reads x 42 times. And although this loop doesn't modify global memory, it does modify variable I here, which is live at the header. It's defined here, and this is the header of the loop. So in this case, because this loop modifies a variable that's live at the header, we cannot employ the spin-assume transformation. But of course, in this case, that is fine, because this loop will anyway execute a finite number of times, and we want to explore it until the end. So these two conditions are adequate, but we would also like to relax them a bit. And for example, we would like to relax the first condition in order to be able to soundly bound loops like this one. This loop tries to atomically increment the variable x using a compare and swap instruction. So it first reads x to a, and then it tries to do a cas. That is, it reads x, and then if the value read is equal to a, it assigns a plus 1 to x atomically, and it tries to do this action atomically, and if this succeeds, then OK is true. Now, if this cas fails, then it just repeats the same procedure until this succeeds. So for this loop, we cannot actually employ the spin-assume transformation because of the first condition, because this the code of this loop here potentially has side effects. So this cast instruction may modify global memory. But if we take a closer look at the control flow graph, we see that if we do reach, if we perform a full iteration, we do reach node 1 again, then it's certain that the cast has failed. This is actually denoted by this assume statement here. Right? If the cast succeeds, then we'll exit the loop. So we can actually relax the first condition and only require that global memory is unmodified along paths that will get us back to the header. We call these paths looping paths. And since this loop does satisfy this condition, and of course it doesn't assign any variable that's live at the header, then we can still do the spin-assume transformation and effectively transform this loop into a read, followed by a cas, followed by an assume statement. Now, as far as the second condition is concerned, the reason why we would like to relax it is to capture loops like this one. This is basically a modification of the do-while loop that I showed you before. It reads x, and then if the value read is 0, it keeps reading x until it reads a non-zero value. But now we cannot do a spin-assume for this loop because the loop modifies the variable a, which is live at the header, which is node 2 here. And what we can do to get around this problem is employ a bisimilarity argument. Now, in this program, these two instructions here are actually bisimilar. Or in terms of the control flow graph, node 2 has two predecessors, both of which get us to node 2 with the exact same edge. So what we can do is employ a bisimilarity argument, delete node 4, and make all of nodes 4 predecessors, that is node 2, point to node 1, and have this, this control flow graph here. But in this graph, there is no variable that's live at the header. Yes, there's no variable that's live at the header, and the loop doesn't modify any variable that's live at the header. So in this case, we can do the spin assume transformation and effectively transform the loop into one read followed by an assume statement again. So with these two arguments, with this spin assume transformation and with this bisimilarity argument, or a similar argument called loop rotation, we can actually handle a wide range of different loops, but we cannot actually handle loops that are potentially effect-free. That is, loops, the iterations of which might lead us to the same state, but we don't know this statically. Sometimes this is impossible to know, and one example is this one. So in this example, the value of z is not known statically. This, for example, might depend on the context, might be assigned by other threads, and so on. And what this loop does here is that it first reads z, and then does a cas on x and stores the result in b. And it repeats this action if the value read for z is the same as the result of the cas. Now, the problem here, and the reason why we cannot do spin assume, is that if we complete a full iteration, we do not know if the cas has succeeded or not. Depending on the value read for z, it might be the case that we go back when the cas succeeded, or that we go back when the cas failed. So we cannot employ the static spin assume transformation. However, what we can do instead is employ spin assume dynamically. We call this transformation dynamic spin assume. And what this means is that we can modify the underlying DPOR algorithm so that whenever it reaches the header of the loop, it checks whether the previous iteration had any side effects, and if it didn't, then it drops the execution. So in this case, when we execute the first iteration of the loop, if we end up back in the header of the loop, and if the instructions that we executed in this path had no side effect, then we can immediately drop the execution. And again, this is equivalent to bounding the loop using a bound of 1 in many cases. So does this also mean we can have stores within a loop? The answer is yes, under some conditions, and I'm going to show you this with an example. So this code here is extracted from the Triber stack benchmark. It's from the push method of this benchmark. And what the code here does is that it first creates a new node. This allocates new memory on the heap. It assigns a new value to this node. Then it reads the alt top of the stack, changes the next pointer of our new node to point to the alt top, and then it tries to change the top of the stack, if it hasn't changed in the meantime, to our newly created node. Of course, if this fails, then it just repeats this procedure. And here's the condensed control flow graph for this program. Now, this is our loop. And in this case here, this cas poses no issue, because we know that if we get back there, back to node 1, this assume says that the cas will have failed. And the actual problem is this store, because this store actually stores to heap memory. But this is okay as long as the stores like this one are not visible to other threads. In this case, this store is, of course, not visible to other threads, because this has been newly allocated by the thread trying to push something to the stack, and it hasn't been connected to the stack itself, so other threads cannot see this. So if we dynamically check that stores within a loop are not visible to other threads, then we can still do spin assume, this dynamic spin assume transformation, and soundly bound loops like this one. So by lifting spin assume and by doing it dynamically, then we have yet another range of loops that we can effectively handle. And now the last category that I'd like to talk about is what we call zero net effect loops. So zero net effect loops are loops, the iterations of which have instructions that cancel each other out. And these are common when implementing things like reader locks. And here I have an example of such an implementation. So X is our lock. This is our locking method. Then there is some critical section, presumably, and this is our unlock. So what this lock does is that it tries to atomically increment X. And if the value that it read before the increment was 0, then this means that it acquired the lock, and this thread can proceed to the critical section. And when it's done, it can simply reset X back to its previous value. However, if a thread reads something that's greater than 0, then this means that somebody else has the lock, so it will simply decrement X and then try to acquire the lock again. Now this loop obviously has side effects, but these side effects cancel each other out. So if we complete a full iteration, we'll have executed both these two fetch and add instructions, so we'll reach node 1 and we'll reach the exact same state. On the other hand, it doesn't make sense to examine scenarios where the lock acquisition fails, so where we actually loop and go back to node 1. And what we can do about this is employ what we call the zero net effect assumed transformation and effectively remove this instruction from the code. So we remove these edges from the control flow graph. And now this lock method is equivalent to a fetch and add instruction followed by an assume that says assume that the lock has been acquired. And this is actually very, very helpful in practice in reducing the state space for these programs, as instructions like these fetch and add increase the state space by quite a bit. Now, this transformation, however, has one caveat, and this caveat is that it's not always sound. And let's see why it's not sound with an example similar to the previous one. So this code here is similar to the lock method that I showed before. The only difference is that now this loop breaks if A is 42. And now we have another concurrent thread that reads X twice. So what is the problem with this transformation? The issue is that if this instruction here does exist in the code, and if we do examine scenarios where the lock where we actually execute this instruction here, then reading 1 and 0 for these two reads is possible. So for example, this read can execute after this instruction, read 1, then this read can execute after this instruction, read 0. However, if we remove this instruction from our source code, then reading 1 and 0 is not always possible anymore. Reading 1 and 1 is possible, or 1 and something greater than 1, because if this read reads 1, then this guy can also read 1 or read something greater, but reading 1 and 0 is not possible anymore. And what we need to do to fix this is actually check whether the zero net effect assumed transformation is valid at runtime. So what Saver does is that if it notices that there are some concurrent threads observing the value of the lock, or there are some concurrent writes to the lock's location, then it just rolls back the transformation dynamically, and it also explores scenarios where the lock acquisition fails. And then and then with this dynamic validity check and the zero net effect assumed transformation, we can handle loops like this one, but also some loops that we have in the paper that have lock and unlock operations instead of fetch and add operations. Now, the last thing that I'd like to point out before showing you some results is that these transformations do not necessarily apply holistically to a loop. We can apply a different transformation to each of the loop's back edges. And for this, I'm going to use a different example. I'm going to use the DQ method of the Michalis Kokologiannakis. You don't have to read this code. I just want to show you how Saver handles code like this. So the first thing that Saver notices here is that there's this variable called success that's live at the header, and that's modified in the loop body. And to solve this, it does some loop rotation so that the success variable is gone, and that we exit the loop when this cast here succeeds. So it effectively deals with this control flow graph here. Now, this control flow graph has 3 different back edges, this one, and this one. And let's take the first one, for example, corresponding to this path here. So for this back edge, we have a bunch of reads, and so going back, completing a full iteration and going back to node 1 has no side effects effectively. So for this particular back edge, we can do a spin assume transformation and effectively remove it. Moving on to this back edge here, corresponding to this else path here, this back edge is a bunch of reads, a couple of assumes, and then a cast, but we know that if we go back to the header, this cast here has failed. So also for this edge, we can do a spin assume transformation. And finally, for this third path here, we have, again, a series of reads, some assume statements, and then we have a cast that is executed unconditionally when we go back to the header. So we can definitely not do this spin assume transformation. We have to keep this back edge. But what we can do is dynamic spin assume. So if we execute this path and reach the same state, and this cast fails, then this means that we've reached the exact same state with no side effects. The cast failed, so we can drop this execution and reduce the state space by large factor. So by employing a different transformation to each of the back edges of this loop, we get this control flow graph, which is actually very helpful when verifying programs like this. And finally, let me conclude with some results. These are some benchmarks that we tried. We have more benchmarks in the paper. Of course, I'm not expecting you to read this. I'm just going to focus on the reader-writer lock example that I also had in the introduction. This is our tool Saver. This is GenMC, on which Saver is based. GenMC employs a very simple spin assume that can transform some effect-free loops, but not all of them. And this column here is GenMC with this very naive transformation enabled. Well, this column here is GenMC with no spin assume employed and just loop bounding employed. And as you can see, even this very naive spin assume actually reduces the state space quite a bit, but Saver manages to reduce the state space by 3 orders of magnitude. It manages to terminate in less than a second in this case here, where GenMC times out and needs more than 30 minutes. And it does so because it employs both a bisimilarity argument, a spin assume argument, and some zero net effect assume transformation for this benchmark. Now, in conclusion, I presented Saver, which is a Spinloop-Aware Verifier. It incorporates some novel extensions to DPOR, some new transformations like dynamic spin assume and zero net effect assume. Saver can explore exponentially fewer executions than the state-of-the-art. And what I didn't mention during this talk is that Saver and the techniques that I presented also work for a variety of different memory models. So they're not just for sequential consistency, but they can be extended to other weak memory models like RC11 or IMM. And Saver is available as part of GenMC on GitHub. We'd be very happy to receive your feedback and questions on GenMC or Saver.